We're going to do today's lesson without any rehearsal. So we're going to be talking about density, uh, center of mass, and rotational inertia. And this is going to be of non-uniform items. So let's introduce the concept of density. Density is the ratio of mass to volume. So our basic definition is that density equals the total mass divided by the total volume. And this is true if it's a uniform material. So if the density stays constant, if the material is made out of one thing and there's no voids and things like that, then this is going to work out and rho, the density is going to be a constant. And I'll show you how to handle a situation where it's not constant. But I need you to know that density comes in three. Oh, whoops, no, I need to finish my thing here. So if density is equal to the total mass over the total volume, it's also equal to a little differential piece of mass over a little differential volume, however we do that. Um, and we'd used this once before. We did this when we were doing gravity, that we said, okay, if it's equal to the total mass over the total volume, it's also equal to some subset of the mass over some subset of the volume. But today we're going to use this relationship, the fact that the density can be calculated from the total mass and the total volume. You get a number, and that number is a constant, but it's also equal to a differential thing. So we're going to use this in a substitution, a U substitution. And now we need to say that you need to know that density comes in three flavors. The three flavors of density are the volume flavor of density, which we just defined here, whereby rho is equal to the total mass divided by the total volume, or a differential piece of mass divided by a differential piece of volume. It also comes in an area flavor, and that's usually used a sigma here, although you could use rho for all of them, and that's the total mass over the total area, or a differential mass over a differential area. And finally, a length, or one-dimensional version of it, which is usually abbreviated with a lowercase lambda, which is the total mass over the total length, or a differential mass over a differential length. I'll call it x, although you could call it little l if you want. Boy, it sure looks like this thing is not in focus again. I'm going to have to play with this focus a little bit. What did we decide? 22, 23 is looking okay. All right, so this is what we're going to be using to do our stuff today. And let's go ahead, and now we're going to define the things that we're going to be calculating in a calculus way. For example, finding the total mass you would think would just be a number. But if we have any kind of a strangeness, like a non-uniform density or whatever, we can find the total mass by integrating all the differential masses. So that's the first thing. Second thing we're going to do is we're going to look at the x position of the center of mass, and that was defined as 1 over the total mass times the sum over I of all the individual mass bits times their position. But if you move this into calculus land, you're going to wind up with 1 over the total mass times the integral of x dm. It's an integral of over all the mass, and that's the problematic part because we have x, spatial variable, and m, a mass variable, and we're going to use the density concept to change this mass variable into a spatial variable. And finally, moment of inertia did not have a 1 over m in front, but it was just the sum of all the r i's squared times the m I guess. I should have written this the other way. The sum over I of all the mi times ri squared. Now I'm going to replace r with x here in a second. So let's go ahead and do that. Why not? sum over I of all the mi xi squared, which becomes, in the world of calculus, the integral of all the x squared dm. Okay, so we are going to make substitutions using these equations. So again, just to summarize, integral dm gives you the mass. The x position of the center of mass is 1 over that m, integral of x dm, and the moment of inertia is no 1 over m, but the integral of x squared dm. We're going to use these three as we try to solve some problems. So first, let's solve a problem that we already know the answer to. Obviously, something you do to double check your work. Okay, so we're going to find the center of mass of a uniform rod. Find mass, center of mass, and moment of inertia of a uniform rod around its end. Okay, so we have to say what it's around because moment of inertia depends strongly on where you choose your rotational axis here. Rotational axis here, 0 here. This other end will be L, and we'll be using the variable x to figure this out. Okay, so first thing we're going to do is we're going to find the mass, and the mass of this thing is going to be the integral of dm. But since lambda is equal to dm over dx, we can just substitute this in, and that means that dm can be replaced with lambda dx, and we'll put that in over here. Lambda is a constant in this case because we have a uniform rod. Lambda is a constant, so we'll put this in, and that means that our integral is going to be lambda dx. And now we know that our limits of integration are 0 to L. Okay, lambda comes out front, and we have the integral. I know this is really not smart here. Dx, and that's going to be equal to lambda L when we put our limits of integration in. Now that doesn't look like the thing that we know, but lambda itself is also the total mass over the total length. So let's put that in, and that's going to be the total mass over the total length times L, and the things cancel out, and we get back our total mass. Okay, so in this case, it's just proof, because the uniform rod is boring. Lambda is a constant, so m does equal m in this case. Okay, trust me, we need this later. All right, let's find our x position of our center of mass, which is going to be 1 over this m, which we now know we can just use m for, and then the integral of x dm. We'll make the same substitution here. I'm gonna have to worry. I'm getting a little close up there, so I'm gonna move down a little bit. So we're gonna have 1 over m, and then we're gonna have the integral of x, and then lambda dx, and that goes from 0 to L. Go down a little bit more. 1 over m. This is going to be the 1 over m. Lambda comes out, and we have x squared over 2. Yeah, that's going to work. X squared over 2 from 0 to L, and I stalled out there for a second, folks. Sorry. 1 over m lambda L squared over 2, and that's going to be 1 over m over L squared over 2, and everything cancels, leaving us with L over 2. That's what I expected to get. Sorry, folks. In the middle of that, I started thinking about moment of inertia. Well, this camera seems to be tilted. That's what's going on. I'll fix it later. Okay, finally, our moment of inertia, the moment you've been waiting for. That's going to be the integral of x squared dm. We're going to put in lambda dx. we're going to pull the lambda out front. We're going to get lambda times x cubed over 3, evaluated from 0 to L. That's going to be m over L, that's the lambda, L cubed over 3, and that's going to be 1/3 m L squared, which is what we knew it would be. Okay, so that's practice, other than my vapor lock in the middle of this line right here. That's practice on how a uniform rod works. It also shows us that these equations here are correct, the ones from the previous page. This stuff here, that's what we do. Okay, so I guess the moment of truth. How do you handle a non-uniform thing? And by the way, as an added bonus, just for fun, maybe we'll try to do the uniform disk, because then it's not a linear density, it'll be an area density. All right, so let's do a non-uniform disk. Sorry, non-uniform rod. Now, I have to make up a density function. You see, there will be a function for density. Now, and so I'm just going to go ahead and say that the density is going to be a times x squared. A is some sort of constant. I don't know what it is, but the density is proportional to how far along you are squared. I could have made this x. I could have made it any function I wanted. I could have done cosine, whatever. I just picked a polynomial. And that means that this particular rod, which has an overall length of L, by the way, and is going to be rotating around this end, it is not very dense at this end, and it is very dense at the other end. So if I was going to put little dots in here, I would have so many dots at this end that it's practically shaded in, and then less dots as I went that way. So something that's much heavier on one end than the other is what I'm saying. Okay, let's go through our stuff here. Let's change colors, have some fun. First of all, we don't know the overall mass of this rod, but we can find it out. The overall mass of this rod will be the integral of dm. But in place of dm, we're going to put lambda dx. But lambda is a function, okay? So that means that dm is going to be replaced with a x squared dx. All right then, that means that we're going to have the integral of a x squared dx, and now that's integrated from 0 to L, which is a times x cubed over 3, evaluated from 0 to L. I think the square brackets are what I was taught in calculus class, so we're okay there. So that's going to be a L cubed over 3, and that's going to be our total mass, L cubed over 3. Okay, it's interesting, but we don't know what units A are in, so this could work out. I guess A has to have units of, I don't know, mass divided by length cubed. So A in units of kilograms per meter cubed. That's the only way this is going to work out to give us a kilogram answer, right? 3 doesn't have any units, but this top has to work out to be kilograms, so that's how it has to happen. All right, let's do the x center of mass. The x center of mass was the integral of x dm, but we're going to replace dm with ax squared. So x times ax squared dx, and now the limits are 0 to L. So that's a comes out. We have x cubed dx. You can see why I chose a polynomial. The calculus is not that hard. The idea is you get this weird stuff. Okay, so that's going to be a times x to the 4th over 4, evaluated between L and 0. So that's going to be a L to the 4th over 4. And what are we going to do? Oh, I forgot the 1 over m out front. My gosh. Confusing. For m. But m is this thing over here, so let's go ahead and put it in. So that's going to be L a to the 4th on the top, and a 4 on the bottom, and then a L cubed on the bottom and a 3 on the top for a grand total of A's cancel, L's almost cancel 3/4, L. Well, that's interesting. Our center of mass is going to be here about 3/4 of the way down. That makes a lot of sense. When one end is much heavier than the other, the center of mass shifts. Awesome. Awesome, awesome, awesome. All right, let's do our moment of inertia, which doesn't have the 1 over m. Integral of x squared dm. And that gets the substitution. Integral x squared a x squared dx. And that's going to be a comes out front. Integral x to the 4th dx. A times x to the 5th over 5. Evaluated between 0 and L. I think we all know where this is going. A L to the 5th over 5 is our moment of inertia. Again, we didn't get to divide by m like we did here, so we don't get this really cool cancellation, but this is the moment of inertia. If this was a 1 meter long rod, then we'd be talking about just this, whatever this constant a is, divided by 5. All right, so that's how it's done. Maybe we'll do the disc in class sometime. It's really not that hard, and there's a number of places where you can see the derivation. Maybe to make this a little better. Okay, so we got time. We've got time here. We'll do one more. Okay, let's do a simpler one, and we'll go a little faster this time. I think repetition helps out here. Non-uniform rod. And this one is going to have a density that's going to be B times X. Okay, not quite a severe difference in, I think this one was actually in the AP test one year. Not quite as severe a tapering of mass as the other one, but let's go ahead and do it. So remember that lambda equals B times X. That means that dm equals lambda dx, which is equal to bx dx. Ooh, I don't like this pen. This is fat fingers. Here we go. What's the mass of this thing? Well, the mass of this thing is integral dm, which is integral of lambda dx, which is the integral of bx dx, which is b times x squared over 2, evaluated 0 to L, which is b L squared over 2. Okay, our position of the center of mass. Remembering the 1 over m this time. My God, Armin. Didn't remember the x. It's early. Gosh darn it. It'll be 7 o'clock soon. I'll reheat my coffee and get that going. Okay, 1 over m, b over m. Integral of x squared dx is x to the cubed over 3, 0 to L. So that's going to be b L cubed over 3m, but m is itself b L squared over 2, so we have b L cubed over 3 b L squared, and a 2 comes onto the top there, so this is going to be 2/3 L. So that's where the center of mass is, about 2/3 of the way down this rod. Excellent. And my moment of inertia, integral x squared dm, integral x squared bx dx, which is b times the integral x cubed dx, which is b times x to the 4th over 4, 0 to L, or b L to the 4th over 4, and of course b must have units here that cancel this out and leave us mass. So B has units of kilograms divided by, looks like length squared. There we go. Okay, that's the lesson for today. Thanks for paying attention. This kind of thing comes up occasionally. I don't think we had any homework on it, but there it is.